All right, guys, last topic that we're going to talk about is similarity in right triangles. So we'll call this right triangle similarity. We already talked about this briefly when we were talking about indirect measure, because whenever I have that shadow reflection that we do, or like a mirror reflection or a bounce, we're always getting these two right triangles, and we get this similarity for those. And we're going to do that on page 71. And that's it. Now the thing is, this right triangle similarity is a little bit trickier because we're going to put the right triangles on top of themselves. So sort of like with the shadow, but not quite. So really what happens with this sort of similar right triangle is if I take a right triangle and from the 90 drop an altitude. Because what happens then, and I think I actually want to start down here and kind of show you this. So if I do that sort of thing and drop this altitude down, what I really get are three right triangles. I have this small right triangle over here. Let me redraw because, again, it can be helpful to see. So that's W, Z, X. So we're kind of pulling this little right triangle off over here. We also have this middle right triangle, like the medium right triangle on this side. So X, Z, Y. And then you have the whole thing. So maybe to add a little bit of color here, like I took this inside guy and redrew it here. And then the other half of that is also a right triangle. So over here, and we drew that guy over there. And lastly, the whole right triangle itself, like the big guy that's around both the other two. Thing is, the right triangles are all similar to each other because they all have a right angle. So you got your one angle down, and they all share angles with each other inside of this triangle. So that's how we get our second angle. Also, like, because there's only 90 left for the other two, it's much easier to get angle-angle similarity here because one of them is definitely already accounted for as 90. So if I take and write out the similarity statement for these three right triangles, if I start with the small one, if I call it Z, W, X, this is where this can get tricky because you have to travel the same way. So I started at the 90 to kind of make it easy for myself, and I went across the smaller side and then the hypotenuse. So I have to do the same thing on this triangle, the middle triangle. So I need to start at the 90, so Z, travel across the smaller edge, and then the hypotenuse, so Z, X, Y. And then for the pink triangle, the whole thing, we can do, so we got to start at the 90. Which on this one is not Z, it's X. Then I got to travel across the small and then the hypotenuse. So X, W, Y. Okay, so once you have that, once you know that they're similar by angle, you can set up a lot of proportions by using H to represent like hypotenuse to hypotenuse, and then maybe small leg to long leg. Sometimes I'll go small, medium, large, but the large is the hypotenuse here, so maybe it's better to go hypotenuse, small leg, long leg. And we have all these different proportions that we can write here. So kind of going off of that, we can do this thing called a geometric mean, which is kind of weird. Like a geometric mean on its own is a thing. The definition of a geometric mean is just where I take two numbers, multiply them, and then square root it. And I get a geometric mean that kind of appears when I have this similar right triangle stuff going on. And that's because of the way it's all proportional. So like when I set up small to small, long leg to long leg, and hypotenuse to hypotenuse, something that happens is that the altitude here that's really drawn inside my right triangle can be written as, so if I go small over long, looking at this triangle here, the small leg is A, the long leg is X, and then when I look over here at this triangle, the small leg is X and the long leg is B, and so when I cross multiply, I get X times X, which is that X squared thing again that we talked about before, equals A times B, and then to solve for X, in this case we can just square root because there's only one of them, and so that's how we end up getting the square root of two numbers being multiplied. I wouldn't worry about like the fancy language that I used here. The way I always remember this is that the altitude of the triangle is equal to the square root of the two pieces of the hypotenuse. So two pieces of hypotenuse, because that's all that is. Like the altitude is equal to the square root of the two pieces of the hypotenuse. Now the other, well actually let's do that one first. So if we open that one up, all of these are good examples of that because the altitudes are all labeled. Okay, so we can just do altitude equals square root of the two hypotenuse pieces. So X equals the square root of 2 times 50, which 2 times 50 is 100, and the square root of that is 10. So that means that that's 10. And if you think about writing the ratio, it works because like 10 over 2 is 5, and 50 over 10 is 5. So there you go. Again, on this one, we'd have altitude equals the square root of the two pieces. So X equals the square root of 8 times 10, which is the square root of 80. And then we talked about this, I think, at the beginning of the year, kind of briefly. Like we can simplify a square root by breaking it back up into its factors. So like I could turn it back into 8 and 80, but I couldn't square root either of those. So a different way to break up 80 is 16 times 5. And that's kind of nice because I can square root the 16, and it's 4. And I can't the 5, so I'll just leave it. And then the last example here is a little different. Even though they label the altitude as a number, I'm still going to set up the same equation. So altitude equals the square root of the two pieces. With this one, I just have to solve. I have to like unbury the x. X was already solved for over here. I just needed to simplify what the square root was. In this case, I think I need to actually get rid of the square root. So 36 equals 8x, and then divide the 8, which 8 won't go evenly, but we can reduce. Like 4 will go into both, 9 times over 2, so 4.5. Okay, and I just like to go right to the formula rather than remembering all the ratios. I just like to do the geometric mean formula. So if the altitude is labeled, you're going to do altitude equals square root times the two pieces. If the altitude's not labeled, you might want to rely on your proportions, but there is another formula for the legs. So if the altitude's not labeled, and instead one of the legs of the big triangle is, the other geometric mean formula that you get is leg equals the square root of the piece of the hypotenuse and then the whole hypotenuse. So piece of the hypotenuse times whole hypotenuse. And I'll put h behind each of those so we remember. So piece of the hypotenuse, whole hypotenuse. So if we take a look at an example of that, now y is the altitude. So I could go straight for y first and do altitude equals the square root of the two pieces. So 3 times 12, so 36. which is 6. If I want to solve for a leg, though, so one of the legs of the triangle, like the big right triangle, let's say I want to solve for x first. Our leg geometric mean theorem is leg equals the square root of the piece of the hypotenuse that is closest, so 3, times the whole hypotenuse, which is 15, because we had to add them up. So we get x equals square root of 45, which I can split that up because 9 times 5, so 3 root 5. And then over here when I solve for z, again, z is a leg, so we're going to do that leg theorem, which was leg equals piece of the hypotenuse times the whole hypotenuse. So z equals the piece of the hypotenuse, so 12, times the whole hypotenuse, which is 15. And so if we multiply those up, actually, I'm not going to multiply those up. I'm going to break it up right now, like 4 times 3, and then 3 times 5, because then that's a 9, and that 9 times 4 is 36, and the square root of 36 is 6 root 5. That was kind of wild. So one other one, and this one I'll just go right in order, because you can solve in any order, it doesn't matter. So if I want to solve for x, that's a leg. Leg is equal to the square root of the piece times the whole. Oh, I got to add those. And I don't know how much y is, so I don't think I can solve this one yet, because I need to know how much y is. Okay, maybe let's jump over and try to solve y next. Okay, so to solve for y, I could, well, I can't do z, because that's going to use y as well. So I could probably do the altitude thing. So if I use the altitude one, then altitude is equal to the square root of the 2 pieces, and then I can solve for y, so that's good. Okay, so we'll square both sides. 64 equals 6y, then divide by 6, which it won't go evenly, but I can reduce for 32 over 3. Then I got to put it in up here. So square root of 6 times 6, which will be 36, and then 6 times the 32 over 3, because like we're plugging that in. Well, the 6 and the 3 can reduce to 2, and then times 32 is 64. Oh, and then if I add those up, that's 100. So x is 10. Now, over here when I solve for z, z is a leg, and so I'm going to do square root of the piece times the whole. So I do need to use that 32 over 3 again. So z equals the square root of y times the whole, which is 32 over 3 plus 6. Oh. So if we do that, when I multiply 32 by 32 here, we're going to get a big old number. My goodness, Siri, where are you? So 32 times 32 over 9, then 32 times 6, but I can divide the 3 into the 6, so really just 32 times 2 is 64. Then I gotta add here, oh my word, what a hot mess. Although, let's see, no, it's not going to, but yeah. So let's do 64 times 9 so that we can add these. So if I change this so that it's over 9, it'll be 846 over 9. Plus the 1024 over 9. And we get 1870 over 9, which I can square root the 9, and that's 3. I wonder if I can square root 1870. Like, I'm just not sure about that. So let's ask my calculator. So 1870, and if I square root it, poop. Sure doesn't. So we'll just leave it square root of 1870. there we go. That's tough.